Hello, welcome to Proton NMR Part 4. In this video, we'll look at the number of neighboring protons and connectivity, and that will be the information we're getting through our multiplicity or splitting patterns. And so this is going to be part of the key information obtained in the 1H NMR. I'll look at simple cases really only, so that way the N+1 rule for multiplicity applies. We won't look at any cases in this video where there's diastereotopic hydrogens or alkene diastereotopic hydrogens other than aromatic hydrogens. We'll keep it for simple N+1 rule cases only for the scope of this video. We'll look at Pascal's triangle to use as a reference for peak height ratio when you look at your sort of the fine structure within each signal, the fine splitting patterns. And you can use Pascal's triangle to kind of sense whether it's a 1-to-1 peak height ratio or a 1-to-2-to-1 or 1-to-3 to 3-to-1, depending on what peak pattern you have. And then we'll do a few example problems. All right, so multiplicity is number of protons on adjacent, which are vicinal carbons, nitrogens, oxygens, or even on the same carbon, which are geminal, if they're non-equivalent. In the simplest of terms, multiplicity indicates the number of protons, as I said, on adjacent atoms. Okay, and those atoms could be carbons, oxygens, nitrogen, sulfur, you name it. Usually we're talking about carbon, oxygen, nitrogen for most simple molecules. Okay. Simple case, the N+1 rule for multiplicity, where N is the number of adjacent protons. So we're going to do an example in a moment. The complex cases, protons on the same carbon that are diastereotopic will also be split by one another because they're not NMR equivalent. And so they're going to have a different N+1 rule. It's going to be N+1 multiple by or multiplied by N+1 for every set of protons that diastereotopic proton sees. So it's a little bit more complex and you get some really complex splitting patterns. We're just going to focus on the simple ones. The example of a simple case I have here is for diethyl ether. And I've shown the two sets of hydrogens. Because of symmetry, you can basically kind of split the molecule in half and it would just mirror itself on the other side. And so if you look at the blue hydrogens here, this is the CH3, the number of adjacent hydrogens on the adjacent carbon would be 2. And so N would equal 2 here. 2 plus 1 equals 3. 3 corresponds to a triplet. And so that's the splitting pattern you expect for the CH3 here. Now, what's the splitting pattern for the CH2? Okay, these two hydrogens C, and these two hydrogens are equivalent to each other. And so they're not going to split each other. So these two hydrogens C, the 3 adjacent hydrogens there. And so N is going to be 3 here. So 3 plus 1 equals 4, and 4 corresponds to a quartet. And so the splitting pattern for this set of hydrogens is going to be a quartet. And this is the pattern, the signature peaks in multiplicity of an ethyl group. So when you have an ethyl group, you're always going to have this triplet and quartet signature peak showing up in your proton NMR. Okay. So here's the NMR for diethyl ether, and you can see I've expanded the 2 peaks. And so these are just the expansions here. And you've got a triplet here. And so this one is going to be, and we'll even go ahead and assign the rest of it. So let's call this peak A and this peak B. A is a triplet. And it's easy to abbreviate that. So often it just gets abbreviated as T. And it's a 3 hydrogen integration. So there's 3H triplet, right? This one here is a quartet. sometimes it gets abbreviated as Q, and there's 2 hydrogens giving rise to that peak. But there's 3 neighboring hydrogens that give rise to its splitting pattern, okay? So the integral is the number of hydrogens that give rise to the peak, and the adjacent number of hydrogens is the number of hydrogens that give rise to the splitting pattern because of the n+1 rule. And so you can see here, you've got a quartet. This is a 1 to 3 to 3 to 1 peak height ratio for that fine structure. So if you blow up the NMR, you can really see the fine structure of the signal, okay? And let's look at another pattern here. Let's look at the isopropyl group, a doublet that integrates to 6 protons, and a septet here that integrates to 1 proton, assuming that there's no hydrogen on a carbon here. So if this is a carbon and a hydrogen, then the splitting pattern for this might be greater than a septet, okay? Why is it a doublet and why is it a septet? Well, if you look at this hydrogen, it's on this carbon, and you add up these hydrogens, you get 6. 6 plus 1 equals 7, okay? And so that's going to give rise to a septet. Whereas these 3 or these 6 hydrogens are all NMR equivalent in this structure. And so they're going to see the 1 neighboring hydrogen. So n+1, 1 plus 1 would equal 2. And so that's going to be a doublet. So here's the doublet. Okay. And this is going to be actually a CH3. And let's write it like this, so it's not so confusing. We'll write it like that. So that's the isopropyl CH3s. And so you can kind of just fragment a piece like that. And so that's where we're getting that doublet from. And it's integrated as 6 hydrogens. So you know that those CH3s are equivalent. Now, some cases you might see 2 sets of doublets, each integrated to 3, but that then would say that those CH3s are diastereotopic. Here in this particular compound, if you were to replace the hydrogens here with deuterium, and then do it again for here, you'd have a CD3 versus a CD3, and you're going to get enantiomers out of that because you would just create the 1 stereocenter there. So those are enantiotopic CH3s. I'll just write that. They're NMR equivalent. Okay, now you go over to the other peak, the one that's closer to the chlorine. So it's going to be further to the left because it's in a more electron withdrawing environment. And you can look at the number of signals here in the fine structure. You get 1, 2, 3, 4, 5, 6, 7 peaks in that ratio, and that peak height ratio that is characteristic of a septet. So there's 7 lines there that give rise to that 1 signal. Okay, that's 1 signal, 1 peak. That's the fine structure or its splitting pattern. And so that's because of the 6 neighboring hydrogens. So this is a pretty good isopropyl pattern that you would see. Now it can vary a little bit depending on what else is attached to this carbon right here. You know, if this is a carbon with hydrogens, then, and if there's a stereocenter somewhere, then these become diastereotopic and things like that. So it can get complex. All right, so here's a pretty easy one. This is a signature of a tert-butyl group. Because the carbon here doesn't have any hydrogens attached, N would equal 0 when you're asking about these 3 equivalent sets of CH3 groups. And so those are homotopic CH3s. I know that because if I replace one of these, let's say I made this CD3, I still don't have a stereocenter right there, okay? Because I still have 2 of the same groups. And so those are all going to be homotopic NMR signature CH3s. And so they're all NMR equivalent. So they all come into the same peak. And so for a tert-butyl group, you always get this really tall singlet that's kind of because there's 9 hydrogens that give rise to this one singlet. Okay, you're not distributing the 9 hydrogen over a more complex splitting pattern. It kind of dwarfs, it makes all the other signals dwarfed, makes them look really small because there's more hydrogens that are going into that little peak. This tall singlet is because of the tert-butyl group. And so, example, tert-butyl-benzene shown here. Okay, so if you look over here, I've got 3 peaks in a 2 to 2 to 1 H ratio, okay, for this integral on around 7 to 8 in that range, okay? And there's more hydrogens, there's less hydrogens spaced out over those patterns. And so they just look smaller in comparison to the tert-butyl, okay? So here's Pascal's triangle, and Pascal's triangle can be constructed if you just always put ones on the outside of the triangle and then fill in the middle with how much this peak plus this peak. If you add those two numbers up, you get 2. And so if you do it again and you add up the inside numbers, so add these 2 up, you get 3. And then if you add these 2 numbers up, you also get 3. But what is it? And so you can see so on and so forth. That's how it gets constructed. What it's really nice for here in the NMR for simple cases is that it tells you the peak height ratio for each splitting pattern. So if you have a singlet, it's just one line, right? But if you have a doublet, those lines in perfect world would be the same height, right? So that would be a doublet. Whereas a triplet, you would see a 1 to 2 to 1 peak height ratio. In a quartet, you'd see a 1 to 3 to 3 to 1 peak height ratio, and so on and so forth. And so if we go back to the isopropyl case, and you look at, let's see, a septet, that's a 1 to 6 to 15 to 20. So that's a 1 to 6 to 15 to 20 to 15 to 6 to 1 peak height ratio for that pattern. You can see that this peak here is 6 times taller than that smallest line, right? So 1 to 6 to 15 to 20 to 15 to 6 to 1. And so the Pascal's triangle is nice to give us a sense for what the peak height ratio should be for those perfect multiplet patterns. Sometimes it's hard to see the low ends of those, right? When you get to these larger cases, it's kind of difficult to see those. They are almost baseline. Unless you blow that up and really expand it a lot, you might get confused. Well, you can always go back to the structure and see how many hydrogens gave rise to that signal and figure it out from there. Okay, so you should be able to look at a structure and know, in theory, what kind of splitting pattern you're getting if you can't see it as clearly in the actual NMR, just because of the baseline peaks and things like that. On the lower field NMRs, so these are where the magnets aren't as strong. We have all sorts of magnets that can be used. On lower field NMRs, multiplets greater than a quartet, they may appear as one peak due to being unresolved, okay? And so you may get less resolution of those signal patterns. In such cases, the peak is often just referred to as a multiplet. But on higher field, more expensive NMR machines where you have much more powerful magnets being used, you get much better resolution of those little fine structure splitting patterns. And so you can see up with ease, even a septet. And so this is a nice NMR where you can see the septet there. All right, so once again, basically I've said all this, but let's just go over coupling rules. Equivalent nuclei do not interact. Coupling constants, we will talk just in brief here, passing. Coupling constants decrease with separation. So typically as you get to 3 to 4 bonds away from something, you're not really going to see the coupling constants for those because they're so small. But coupling constants are these values that tell you if one set of hydrogens is coupled to another. Do they split each other? And if they do, then their splitting patterns should give coupling constants, these numbers, which are basically the distance between each fine line in the peak pattern. And those numbers should be the same for each peak. If they're coupling to each other, they should have the same coupling constant. Multiplicity given by the number of attached equivalent protons. So once again, the n+1 rule for simple systems, but for multiple spin systems, this is when you're going to have diastereotopic hydrogens involved. Then you're going n+1 times n+1 for each different interaction. And so it gets complex pretty quick. The relative peak heights in the area follow Pascal's triangle, and then coupling constants are independent of the applied magnetic field strength. Okay, so let's look at the influence of the magnet field strength on splitting, just to show you what it's like to go from a pretty weak magnet. 100 megahertz is our radio FM dial, right? So this is basically your FM radio frequency. But if you change the magnet, so you go to a much more powerful machine, now we're on the 400 megahertz of the dial. We're not listening to radio stations in the 400 megahertz. But in terms of what it's doing here, let's look. So these 5 hydrogens on the aromatic ring are all showing up as kind of one peak, but these hydrogens are not equivalent to those hydrogens, which are not equivalent to those. So there should be 3 signals in that region. And it's because the field strength isn't that good. So if you put a higher magnet in there, a much more stronger magnet, you're increasing the magnetic field strength and you're going to increase the resolution. So this example for benzyl alcohol, where we know we have 3 non-equivalent sets of protons in the ring, we should expect to see 3 signals, but all the signals are just overlapped there. And so I would just call this a multiplet. And it's integrated to 5 hydrogens, and it's hard to see any pattern. Okay, if you go to the better magnet though, you can see that there are 3 different colors now represented. You can see the 3 signals there now becoming resolved. And so you're going to have here 3 signals seen. If you go to even a higher field, you're going to see those resolve even better. And so that's the advantage of having a stronger magnet. You get better resolution, you get better baseline separation. And so just a better quality NMR spectra overall. Let me just talk a little bit about proton deuterium exchange. So basically there's acid-base chemistry that can go on between different protic environments. And so if you have an alcohol that has this hydrogen here, and you're using a solvent that's deuterated because you don't want the solvent to show up in the NMR, so you use a deuterated one. But if it's a protic deuterated solvent, then you can start to exchange the deuterium in the proton, okay, through the acid-base properties of that. And so you're not going to be able to see this eventually show up. You might see a little bit of it show up, but the integral wouldn't match maybe what it should be. And that's because you're getting deuterium exchanges. Also, hydroxyl groups and amines, not as much as hydroxyls, but things that can hydrogen bond in exchange tend to be broad in the NMR. So you'll see a broad signal usually for those. And the splitting patterns just do not show up well for those hydrogens. They just look like broad singlets, unless you're in a very dry solvent, okay, where you're not exchanging at all. So the splitting of the hydroxyl proton is not always observed. The OH peaks may appear as broad singlets or BS singlets due to exchange. The integration of the OH peak may not be accurate due to exchange with the deuterium. Deuterium is a proton NMR inactive nuclei. Its spin is not equal to 1/2. I believe it's equal to 2 halves or 3 halves actually. So it doesn't have the right spin state of 1/2 to be impacted by the proton NMR. So it's not going to pick up. The chemical shift of the hydroxyl group They can vary. They are all over the place. Depends on a lot of things, concentration, environment, etc. So unless phenolic, you might see it closer to 10, 11, 9, 8. Okay. A common trick to easily identify the OH peak in practice is by adding in a drop of D2O to the sample. Okay. If you add D2O in, there's going to be this rapid exchange of the proton for the deuterium, and that hydroxyl peak will now disappear when you retake the NMR. So you can see exactly which peak was the OH peak by doing that. The technique also works for protons of nitrogen or sulfur as well, because they're also protic. Okay. So that's really something you're not going to worry about right now, but when you go into a lab, or if you need to analyze an NMR and there's these sort of things happening, that becomes important to think about. All right, so from a previous lecture, lecture 42, we have structure D. Let's go ahead and assign now our splitting patterns. Okay, and I already said that we had integrals here also of 3 hydrogen, 2 hydrogen, 3 hydrogen, 2 hydrogen, and 2 hydrogen. And then now let's include the splitting pattern. So here's a singlet. So I'll just say S. Here's a singlet, S. Here's a singlet, S. Here's a doublet, although not perfect peak height ratio. It's because they're leaning. And they're called leaning doublets, but still doublet. It's 2 peaks that you see. So it gets the abbreviation of D. And so that'll be a doublet there. And the last thing we have to do is assign each letter, each peak to the right number of the right set of hydrogens. Okay, so maybe you can do that already. And maybe you can look here and say, okay, this carbon is attached to a carbon that has no hydrogen. So that's going to be a singlet. Okay, so that's going to be a singlet. This carbon is attached to 2 other carbons that has no hydrogens, and these 2 hydrogens are an antiotopic. So they're NMR equivalent, and so it gives rise to a singlet. But which one? That's the next video. Here's a doublet. So you have some symmetry in the ring here. So you can see that there's symmetry. So these 2 peaks, those 2 hydrogens are the same signal. So I'll just label one of them as a doublet integrated to 2 hydrogen. And this is a doublet integrated to 2 hydrogen. And then I have another singlet integrated to 3 hydrogen. So really the question, I think, is which singlet is what, and that will be dependent upon its chemical shift now, unless you can already figure that out, no problem. But it'll be more difficult. So we'll continue this problem in the next video. Here's another one. Here's a constitutional isomer of structure D, and you can see that its NMR is different, right? So now I have more peaks. I have more non-equivalent sets of hydrogens. I have different splitting patterns, and so on and so forth. So if you look here and you blow that up, you can see that peak B here, 1, 2, 3, 4, 5, 6, that's a sextet. You have a singlet around 10. So I am going to tell you here that this is, we'll call F. Okay, and I'll let you figure out the rest on your own. I'll return to this at a later time. So can you go ahead and assign each letter, each peak to the right set of hydrogens, okay, using the information that we have available to us. All right, here's another practice problem. For each structure, assign the multiplicity of each non-equivalent set of protons indicated. The answer for structure 2 will be shown on the next slide. Okay, I'm going to do structure 1 as an example just to kind of go through this again. So I'm going to pick A first. A is next to a carbon. That's a CH2, and so N is equal to 2. So that should be a triplet. Okay, if we go to peak B here, it's next to a E and C, and there's 4 hydrogens total. So N is equal to 4. So that should be some sort of a pentet or a quintet. Okay, and then for C, also a quintet, because the N is equal to 4, there's 4 adjacent hydrogens next to C. D, there's just A next to it, and A has 3 hydrogens, so N would equal 3. 3 plus 1 is 4. 4 is a quartet. And you can say Q for that one. E is next to B. The oxygen has no hydrogens, so E is next to B. B has 2 hydrogens, so N is equal to 2. And so E should be a triplet. And then finally, F is next to the chlorine. There's no hydrogens there. It's also next to C, and there's 2 hydrogens there that are equivalent to each other. And so F is going to be a triplet as well. Okay, so I'll let you do structure 2. The answer to this is shown on the next slide. So right now I've skipped over that slide, and you can see here now that these are the NMR structures predicted by ChemDraw for structure 1. And you can see that the splitting patterns that I predicted match the splitting patterns that are showing up as well. This is an actual predicted structure by NMR, by ChemDraw. I didn't go into the lab and take this NMR. I built it using ChemDraw, but it's pretty accurate for simple cases. I've also shown the NMR structure, the NMR spectra for structure 2, so you can compare what you determined in this problem to see if you're right. Okay, and so that'll give you a way to kind of check your work as you go as well. Okay, so that ends the lesson here. I hope this was helpful for you, and thank you for your time.